Despite the rule of powerful predictive analytics, it is important to not overlook the importance of descriptive analytics, which provides organizations and their users with the ability to understand data through well-designed reports, dashboards, and visualization tools. It helps people comprehend the data, as most people have difficulty processing information provided by data in its raw forms, such as spreadsheet and database tables. Descriptive analytics is a process that involves organizing, tabulating, and visualizing data to summarize what has happened in the dataset. Reports such as financial reports or dashboards for public health stats, pandemic outbreaks, or crime rate across regions and time are all examples of descriptive analytics tools that make it easy for humans to digest large datasets in an efficient and effective manner. While descriptive analytics can take many different forms, in this lecture we are going to focus on data visualization to show how tabular and graphical tools can help us organize and present data. Let's start by looking at graphical method for visualizing one variable. The tools for visualizing a single categorical and numeric variable are different. So let's first focus on a single categorical variable by looking at this example. Suppose the HR department of a large technology company is trying to understand its sales professionals' personality types according to the Myers-Briggs personality test, a self-assessment tool that's often used in the industry. A total of 1,000 employees who took the test reported various personality types. In its raw form, the data would be a 1000 by 2 table, shown in Table 3.2, that records the personality types of the 1,000 employees. However, it is of limited use to someone who wants to understand the data. If we summarize the dataset by counting the number of employees that fall into each personality type, we have constructed a frequency distribution table as the one in Table 3.3. Now the data is a lot easier to digest because it summarizes the frequency and the relative frequency of various personality types. We can easily see that Explorer is the most common personality type, whereas Analyst is the least common. However, we can go one step further by creating a bar chart out of the frequency stats, as in the figure. The bar chart, sometimes also called a column chart, visually represents the data. The height of each bar is equal to the frequency of each personality type. The figure allows us to not only find out very quickly which personality types are the most frequent and the least frequent, but also the differences between all the personality types in terms of their frequency as well. As you can see, the appropriate visualization can pack a lot of information and convey them effectively to the intended audience. Later, we will demonstrate how to construct a bar chart or column chart in R. Now let's look at how we can effectively visualize a single numeric variable. A frequency distribution groups data into intervals and records the number of observations that falls into each interval. In this example, we have the annualized returns of growth mutual fund and the value mutual fund over a 35-year period. Let's focus on the returns of the growth mutual fund for this example. The data in its raw form in Table 3.1 is again very hard to decipher, as the users are often bogged down by the details and the amount of data to process. However, by grouping the data into intervals, we can convert the data into a frequency distribution table as the one in Table 3.6. The frequency distribution table draws our attention to some key points in the data effectively. For example, we can learn that the most common historical returns for the growth mutual fund is between 0 and 25%, followed by 25 to 50%, suggesting that a higher likelihood of positive returns on the mutual fund. You can increase or decrease the number of intervals, or widen or narrow the interval width as needed to drill more into the data. A graphic representation of the frequency distribution is called a histogram. Histogram is the counterpart for numeric data to the bar chart for categorical data. In a histogram, the width of each bar represents the interval width, and the height of each bar represents the frequency. As you can see from the histogram in this slide, it packs a lot of information in a simple graph, including the range of the data, frequency distribution, and the relative frequency of the intervals, and communicates what's in the data effectively to the intended audience. In addition to information on the range and frequency distribution of a single numeric variable, the histogram also provides information on the shape of the distribution, which in some cases can be very important to data analytics. The shape of the distribution can be categorized as either symmetric or skewed. A symmetric histogram is a mirror image of itself on both sides of its center. It would create a bell-shaped curve that is called normal distribution. The histogram A in this slide shows a symmetric distribution, which has a normal distribution if its edges were smoothed. Histogram B in this slide shows a positive skewed distribution. A positive skewed distribution suggests that there are a small number of relatively large values, as shown by the long tail on the right side of the graph. In a positively skewed distribution, the median is less than the mean of the values, as the relatively few outliers inflate the mean of the dataset. Histogram C in this slide shows a negatively skewed distribution, which has a long tail extending off to the left, suggesting that the presence of a small number of relatively small values. In a negatively skewed distribution, the median is greater than the mean of the variable, as the few very small numbers would deflate the mean of the variable. Knowing the shape of the distribution allows us to gain a better understanding of our data and any data quality issues that may exist. Some statistical and data mining methods would prefer a symmetric distribution, and some mathematical transformation techniques such as log or square root transformation can be applied to convert a skewed distribution to a symmetric distribution in the data. We will look at how we can create a histogram in R later in this lecture. So far we talked about how to visualize one variable, but rarely would a dataset come with only one variable. Therefore, we need to understand the tabular and graphical tools for exploring multiple variables. Inspecting multiple variables adds another dimension to our understanding of the data, which is the relationship between variables. Now let's focus on how to visualize two categorical variables first. We can use a variation of the bar chart called the stacked bar chart to visualize two categorical variables, as in this example. In this example, we have included another categorical variable, sex, in our personality type dataset. Table 3.9 in this slide shows a contingency table that shows the frequency of personality type and sex. For example, 55 female employees have the analyst personality type, whereas 61 male employees fall into this category. The contingency table can be easily constructed by either manually tabulating the numbers or using the pivot table function in Excel. It helps us understand the relationship between the two variables, personality type and sex, and answers the question of whether the sex of the employee has any impact on his or her personality type. An even better or more intuitive way to answer this question would be by the stacked column chart, as the one in this slide. The chart not only shows the distribution of the personality types, but the composition of male and female employees within each category. This chart clearly shows that no discernible differences in personality type can be found between male and female employees. We will later look at how we can construct a stacked bar chart in R. Finally, let's look at how we can visualize the relationship between two numeric variables. The most common way to visualize two numeric variables is using a scatter plot. The diagrams in this slide are all scatter plots. As you can see, in a scatter plot, each point represents a paired observation for the two variables x and y. The variables x and y can be anything. They can be the income and age of a customer, cost and price of a product, or the trading volume and the price of a stock. By plotting each observation based on the numeric values of the two variables x and y, we can easily understand the relationship between x and y through the scatter plot. For example, in the scattered plot A, we see two variables with a linear relationship as shown by a straight line, which suggests that a given change in x will always produce a corresponding change in y. Scatter plot B shows a non-linear relationship, as a given change in x does not produce a constant change in y. In this case, as x increases, y would increase exponentially. Finally, in scatter plot C, it shows no relationship between x and y, as changes in x do not translate to any change in y. Scatter plot is extremely useful in helping us understand the relationships between two numeric predictor variables, and between predictor and target variables. It helps us detect any predictor variables that may be irrelevant to predicting the target variable, and identify redundant information that exists between predictor variables. In addition to the three relationships that are shown in this slide, many other forms of relationships between data can be detected by a scatter plot. We will demonstrate how to plot a scatter plot in R later in this lecture. So to summarize, tabular and visualization tools are important and effective to help us understand our data. They are especially useful in descriptive analytics that is often performed before more sophisticated analysis such as predictive or prescriptive analytics are performed. It is a critical step in the data understanding phase of many data mining processes.